Hi, this is a rough estimate of how precisely you could scan the interior of the Sun, Moon, Earth, Venus, Jupiter, and a special region if you needed it. Using several different networks. One is a relatively small one. It's LIGO operating at high sampling rate. They have 16,384 samples per second, and they basically have one channel is all that they're using. Um, Unfortunately, they only have one. Well, actually, they have two seismometers that can be used as gravimeters, but that really belongs in the iris. This is the seismology group. I'll show it in a minute. So basically, they have one channel, three stations, and I've only seen that they operated for 2 years roughly. So they have this many seconds worth of data at that rate. Now, at this rate, the sample length for the that they're picking up, it's coming in at the speed of light and gravity, which are the same thing. So in the time in 1/16,384th of a second, light will travel 18 kilometers roughly. Okay, so that's it. So now here, what I did was for the Sun. If you let's see what this formula is here. So D7, which is it's actually the size of the Sun plus a buffer. I wanted to get the whole sphere of the Sun plus 3%. We can change that. Okay, and so this is the whole diameter of the Sun. Let's see, and by D21. Oh, and here I'm breaking it up into 10,000 pixels on a side. Okay, so I took the whole diameter of the Sun, added 3% here, 3%, and then divided it by 10,000. So that comes out 143 kilometers. And since each pixel or each sample is 18 kilometers, you divide this by that to get the number of samples per voxel. Okay, so I'm kind of shifting back and forth. It's kind of hard. They really are volumes. I'm using cubes to keep things simple, and also like when I do the calculation, everything is in Cartesian coordinates. So it's I'm not going to do spheres for a little bit. Anyway, so this is there. Now the way I chose these numbers was I basically came in here, and for this one, I just basically wanted to get several samples per voxel per second. So at this rate, in 1 second, you'll get 7.83 samples for that voxel. Now I'll explain how to get the data in there, but this is a rough estimate. So here, I took the Moon is pretty small, so I can get a 45 by 45 by 45 cube, and I can get 4 samples in each voxel, or on each side. So it's this cube for the total number of samples in there, and that will cover the Moon 45 by 45 by 45, and then the Earth there. The Earth, could we? No, that's pretty much it. I mean, this is a low sampling rate in the way I'm aiming for a gigasample per second, or actually terasample per second. We have the technology. Somebody could do it if they were willing. We'll see. So anyway, Jupiter is actually quite large, and here, coming in several samples per side of a voxel. Um, you get 1800. So this is n cubed. Let's see, maybe I can make these a little more apparent. Let's do this way. Okay. All right. So that's how many, and these are whole numbers. So let's go down to get rid of that. Okay. So we got a trillion. Let's see. There's a billion, trillion. You got a trillion voxels to cover the sun if you wanted to. So even with their present capability, they can slice and dice the sun quite a bit, and they still, and they're, if I cube that, so it's about 8, let me just show you the number. So this number here cubed, so there's about 480 pixels going in, or 480 samples every second going into that voxel. The sun is just that big. Now, am I getting this right? Samples per voxel. Yeah, the reason is because the voxels are so big, and our resolution is 18 kilometers, and so we're able to do it. Now, that's not, this is very rough, but that's there. Now, what's going on over here? I thought I'd explain that. One channel, 3 stations, 2 years, 365 days a year, 886,400 seconds per day. That's 189 million seconds worth of data, which if you multiply that by how many samples, so during the second, this is how many samples are going into each voxel, then, is that right? No, I think I got, yes. The reason is, okay, each sample is actually getting used, might get used no, I'll have to, let me do it. This is still rough. Okay, these numbers are pretty close. Okay, these are realistic. So at that sampling rate, you can get this many pixels in there. Let's see what happened here. Now, this one dropped down, so that then they call it decimate. They have some samples that I can get to that are 4,096 samples per second. The raw data is in there at the higher rate, but I might not be able to get to that. So if at that, I can drop this down and still get basically a sample per voxel for every second, and get some decent things. So that basically it drops this down quite a bit, but it's not there. And okay, because you've run, oh, this is wrong. Okay, so this is also 1 channel, 3 stations, 2 years. Okay, so did I get these right? See, D18. Oh, I do have that wrong. So this is 31. So this is D31. Thought it looked a little funny. Okay, still working on this. So what's going on is, okay, so you take this for every second, and basically what you do is in every second you got data. Let's see. Oh, the other way around. Let's see. Yeah. Okay. You move forward a point in time, and yeah. So you're gonna calculate the pixels. Okay. Every pixel. Let's see. No. Yes. There's an estimate of the gravity, a component of it for every voxel in the scan volume for every second. And so you run this, so let's see. It's kind of hard. I have to try to narrow this down. Let me just walk through what I kind of do know. Okay, this is Iris. They've got 3 channels for each of about 200 stations that are able to measure gravity at all. And on average, they're newer ones, and so I just estimated 5 years. There are instruments that have been there 15 years, 20 years, I think, and all. Now, for the most part, the only, you can get like 175 pixels per side on the scan of the sun, so 175 by 175 by 175 cube, and still get roughly a sample per second out of each one. And the other ones not so much. I mean, we're getting just a few. But the thing is you can go. I think what you can do is go in and subsample. Let's see if I can explain this. I'll just have to do it and show you. But even though it looks like this is hope for the sun, you could do it. Iris at 40 samples a second could actually generate a thing. And the thing is you every set of 3 stations in there can generate an estimate. And because their distances are slightly different, what they're scanning or what they get to is slightly different. And I think I can squeeze out something out of that. Now, even a month of data wouldn't be hard, and I just need, what I need is 3. Well, actually, I know the specific direction and distance. Let's see how to do it. So each one is going to have. Let me pause a moment. Okay, here's a little calculation that may help. This number here is twice the diameter of the Earth, so I'm just squeezing it in exactly. The time for light to travel that is 4/100ths of a second, a little over 4/100ths of a second, about. And what I did was I said, what sampling rate do I need to get 1,000 pixels per side? Okay, and then I also want some redundancy, so I actually want to sample it. What I'm going to do is sample it at 5,000 samples per side, and then double up. I'm going to use redundancy in here, so I'm going to combine those. So I can roughly display I can collect and display 1,000 per side. That's a billion pixels in a volume, but there. Now, at one point in time, I go and say, okay, this where is in this case the Earth? Where is a certain voxel on the Earth at this point? Okay, that's what I did. I say, I got 1,000 voxels in there. Okay, or 1,000 times 1,000 times 1,000, a billion voxels. And you take the first one and you say, at this point in time, I'm in the second number 1. Where is that voxel? And how far is it from my stations? I need 3 stations. So I basically look and see, is there a correlation between these things? Now, essentially I kind of hold the Earth rigid. Okay, it's in its cube and it's there, and my station's orbiting. Okay, so in a sense, the station is orbiting this fixed Earth and let's see if I can just, yeah, and or the signals coming into the station are coming in from relatively different directions because it's a rotating frame, and you're looking for the the information that all three of them. So okay, so you got a station over here, okay, and let's make them a cute color. So you got a station there, and a station here, and a station here. Okay, and they're looking at something over here. Okay, so and probably you don't want you hope they're not collinear, but that's all right. Okay, so this one's closer, so it's going to be measuring how it wants 1, 2, 3, 4, 5, 6, 7 sample times back. Okay, so it looks in its record. It's at a certain time. It looks back this many time steps, and says this many samples, and says, okay, record that one. And this one has to go further back. It's because it's further away from whatever it's looking at. It goes back even further because the data from this point originated earlier, and then this one is kind of in the middle in there somewhere. Okay? And those distances are somewhat unique. Now, I don't know. I hadn't done this yet, so I don't know. So I think I'll try to get them scattered around the Earth. There are for the iris, there's 200 stations. Well, to be conservative, say there's just 50 stations, that you could get good data from. Still, you have a lot of data. So I mean, you do this for 1 second. Well, you could do it as well for another second. It's actually 40 samples a second. I've done this on those things, and so probably maybe I need to average, only do this every minute, and it would be like make a video minute by minute of the interior of the Earth for this many voxels. I don't know. Here, 175 is relatively coarse grained, but literally every sample time, you could say for every pixel, what could the contribution be? So you're going to be building up a rather large number of data points that belong to each pixel. Now, I'll have to go through and kind of better visualize the contributions from there, and how do you correlate them and all. Right now, I just want to look at. I'm not even correlating them. I'm just going to collect them and count them, and see. Because a lot of times, if there's no data, or all the problems come out just walking through the basic exercise. So some of this is correct. Some of it's a bit of a stretch. The numbers are right. I mean, if you sample, if you have if you break up light time into, if you are sampling at 16,384, then there will be a pixel size, a resolution of about 18 kilometers attached to that. And then if you have something the size of the sun, it's going to be picking that up. Now, there's radial direction and transverse directions. There's things. This may only work on the Earth for certain kinds of things. I don't know. I just want to give it a shot. Um, let me just stop here and say I'm just too tired. I hope I'm not ignoring. I probably am. I know I'm probably ignoring some really, really basic things. But when you do something like this, you just sometimes you just have to start chunking it. Like you put a spreadsheet together, you start throwing in the pieces, and and see if anything makes sense. I know this is fuzzy, but in general, I know that it's correct. This is the data you have available, and those are the number of seconds of data, and you multiply that by this, and that's how many actual data points are in there. So this is still larger. So breaking it up into what can you do in 1 second, and what can you do, when you add up all the seconds that are available that are there. So that's roughly what I'm trying to do. So, this 189 million times 16,384 is just, it's out of my, let's see, it's rather large. So even only a couple of years, that's, okay, I'll have to do it in scientific forms. Okay, 10 to the 12th. Okay. So there's that many data points in there. So more than terabytes, tera number of those things, whatever that is. So okay. Now this definitely, if I can get this to work at all. Now, when you correlate, okay, one of the you should see their data is funky. They have a lot of instrument noise. They have jigs and jags where they're banging on the to keep things in line and keep them controlled and all. They're just lucky that the signals that are coming in are so large relative to what they're doing that they can do this. They should normally be able to measure background noise a way lot better than that, and they're it's kind of clunky the way they handle it. So I can remove some of that there. I was looking at it and get it to where it's cleaner, because I need all the station stuff out. Now just correlating them, okay, you do this many samples for a voxel in there, so it's for every second you get an estimate for every voxel. So it's kind of thin. I mean, here, let's see, so you got that many things. This is just along the side, okay, so, and then you're spreading it out in 3 dimensions, so maybe I need to adjust a little bit there in terms of the information that's going into it. All right, well, let me stop.